Hello, everyone. Welcome to pre-lecture 18. This lecture is going to cover buffers, and we'll just jump right in. So I guess before we get to buffers, there are a couple things that probably should have included in our last pre-lecture video, but did not. So just wanted to cover those real quick. First is talking about periodic trends with regards to acid strength. And so basically there are two things that we need to consider. And it relates to how easily a bond can be broken between a proton and whatever it is bound to. And so the first thing that we would need to consider is electronegativity. So the more polar our HX bond is, the stronger our acid will be, generally speaking. And the other thing that we need to balance that with is atomic size. And so the smaller the atom, the stronger a bond it will have with it, the proton, H+, and that means that those bonds are harder to break. And so probably the example where we see this most is something like HF, where it's a weak acid, we know, and it's of course not because of electronegativity. The fluorine is our most electronegative atom, but because it's also quite small, the only weak acid in our halogen series, whereas HCl, HBr, HI are all electronegative and quite a bit larger than fluoride, and so they are all strong acids. If we were to compare our chalcogen series, so oxygen, sulfur, selenium, and tellurium, things get more and more acidic as we go down that column because the size of our atom is increasing. Okay, so you should be able to recognize these differences. One thing I will say, I won't ever ask you like, what's the stronger acid between HF and H2TE, because that would be very hard to know. So typically I'll have you compare atoms across rows or across columns, just as a heads up. Okay. The other category that we haven't yet covered are called oxyacids. So these are acids where we have some sort of central atom and then oxygens bound around it. And so you could think of the chlorine oxyacid series shown here, where our strongest acid is going to be perchloric acid because it has the most oxygens. Then chloric acid, HClO3, would be next, which is basically a strong acid, or at least very close to it. Then we have chlorous acid, HClO2, and hypochlorous acid, HClO, that are in fact weak acids. And so you can see that as we add more oxygens, our acids become stronger and stronger. All right, so on to buffers. And so what is a buffer? It is a solution that contains an appreciable amount of both a weak acid and a conjugate base. And so this is what we would call a buffer solution. And we identify them by their resistance to change in pH whenever we add a strong acid or a strong base. And so typically, a buffer will consist of a weak acid and its salt. So an example might be acetic acid, C2H3O2, or sodium acetate, or not or, but and sodium acetate, which is just the sodium salt of acetic acid. And another key point is that buffers cannot be made with strong acids. So for example, you couldn't make a sodium hydroxide HCl or HCl-based buffer because basically there's no equilibrium there, right? We know that things will fully dissociate. So just a colorful example here, we have some solutions, one that is buffered, one that is not, both at pH of 8. When we add some acidic solution to both of them, we would see that there's a very minimal change in the pH of our buffered solution, whereas we get color change due to the presence of an indicator, suggesting that our unbuffered solution changes pH quite a bit. Okay. Right, and so if we're thinking about a buffer on the molecular scale, essentially we want to think about it as an equilibrium, where we have something like a weak acid. Again, this is our acetic acid. reacting with water to form our conjugate base and hydronium. If we have a good amount of both our weak acid and our conjugate base present in our buffered solution, then if we add more hydronium, so in the form of HCl, for example, or an HCl solution, then that hydronium will react with our conjugate base to form more of our acetic acid. So our ratios between the two will shift to where we have more acetic acid present than acetate after we add HCl. But because we still have a good amount of our acetate left over, that means that we'll see a minimal change in our pH. Okay. The alternative is also true, where if we add hydroxide to that buffered solution, it would react with the acetic acid portion of our buffer to make water and then acetate. And so we would see the reverse. We would have more acetate being present. But again, as long as we don't add too much of our base, we would still be able to maintain approximately the same pH. Okay. So, of course, we can do some math related to this. And so let's do an example here where we calculate the pH of a buffered solution that can be determined with an ice table, because of course we are still in our equilibrium unit. And so in this example, we have a buffer containing 0.05 molar propionic acid and 0.045 molar sodium propanoate, the conjugate base of propionic acid. Then we're given a Ka value of 1.3 times 10 to the negative fifth. And so if you want to try and solve this yourself, I'd recommend pausing the video. You can, of course, do that, but I'll go ahead and jump in here. Would always recommend starting by writing your chemical equation here. So we have HC3H5O2. We would say that that could react with water, and it would be in equilibrium with our hydronium, H3O+, and our conjugate base, C3H5O2 minus. Okay, and if we were to make an ice chart, we could fill that in with our known values then. So let me make my lines here. We know that water is our pure liquid, so we won't need to enter any values for that. But then we're told we have a concentration of 0.0500 molar of our propionic acid, and then what's different about a buffered solution is we have an initial amount of our conjugate base as well. So this 0.0450 molar solution. You can assume, since we're not told anything about the pH, that our concentration of hydronium is going to be 0 to start. Okay. Because we have more of our propionic acid to start, that's going to tell us which direction this will go. The reaction will ultimately move towards products. And so we would subtract X from our reactant side and then add X to each of our products that we're forming. So we combine those two terms, 0.0500 minus X for our reactant, and then X for hydronium, and 0.0450 plus X for our product, our propanoate. Okay. You can also write, of course, the equilibrium expression, which is just our Ka, and then products over reactants, so H3O plus, and then C3H5O2, 2 minus, and that would be divided by our concentration of acid, HC3H5O2. All right, and so we can, of course, then plug in these values that we determined from our ice chart and solve for our final pH. And so our Ka is 1.3 times 10 to the minus 5. That will be equal to X times 0.0450 minus X, or plus X rather, sorry, and then that'll be divided by 0.05 minus x. Okay. Oftentimes in buffer solutions, we can make the x is small assumption. So I'm going to do that. I'm going to cross those out. Both the addition and the subtraction of x, we can assume x is small. And so that reduces our equation to 1.3 times 10 to the minus 5 equal to x times 0.0450 over 0.0500. Okay, so pretty simple equation to solve. We just need to do some multiplication, and when we do that, I got a value for x equal to 1.44 times 10 to the minus fifth. And we know that this x value is equal to our concentration of hydronium at equilibrium. And so that means that we can take the negative log, of course, of our concentration of hydronium at equilibrium, which is equal to x. And when we do that, I got a pH value equal to 4.84. So that is how we would solve a buffer system using an ice tray. One thing I will say is that you of course want to check your x is small approximation still. And so if we were to do that, 1.44 times 10 to the minus 5 divided by our initial concentration. Shouldn't matter which initial concentration you use, they're both quite close, multiplied by 100. And I got a percent error of 0.02%, which is of course significantly less than 5%. And so our x small approximation checks out. So that's how you would solve a problem like that. Of course, if you have questions, feel free to email or let me know. We have a little bit more material to get through here, so for that. But another thing to think of anytime you use the Henderson-Hasselbalch equation, or anytime you hear the word buffer, is to use this Henderson-Hasselbalch equation. And so this applies in buffer systems. The reason it works is because our initial concentration is generally approximately our final concentration for both our weak acid and our conjugate base. This is due to Le Chatelier's principle. I'm not going to go in depth into that, but if you have any questions, feel free to ask in class. And the Henderson-Hasselbalch equation is ultimately derived from our equilibrium expression. So if we start with that, we could then rearrange it to get hydronium on one side, our equilibrium constant on the other. We were to take the log of both sides. That would, of course, be what that looks like. And then if we multiply by -1 and apply those logs, of course, the negative log of hydronium is pH, negative log of Ka is pKa, and then we're left with our log term of our base over our acid, because a negative log with a fraction just flips the sides. Okay? Flips the numerator and denominator, I guess I should say. Okay. Right, so that's how it's derived. And then the last concept we'll talk about, I believe, is buffering capacity. Okay? And so this is the effectiveness of the buffer to resist changes in pH. And the most efficient buffer will have equal concentrations of HX and our conjugate base X minus. Okay? So we say that the buffering range is exceeded anytime we have a ratio of 10 to 1 of either our conjugate base to weak acid or weak acid to conjugate base. This means that if we were to plug in those values into our Henderson-Hasselbalch equation, when we have a ratio of 10 to 1 for our weak acid to conjugate base, that would be equal to pH equals pKa minus 1. Whereas if we have a flipped ratio where we have 1 equivalent of weak acid for every 10 equivalents of conjugate base, then we would have our pH equals pKa plus 1. And so that would mean that for a buffer to be successful, or not exceed its capacity at least, it would have to remain within 1 pH unit of the pKa of the weak acid. Okay? And finally, of course, the larger the concentration of Hx and X minus, the better the buffer will be, or the more neutralizing power we would say that it has. That's it for this lecture. Avogadro says time to get buffered. I hope you have a good day. Thanks for watching. Please let me know if you have any questions. I will see you in class.